When we observe quantum mechanics, we typically look to the physics of the ultra-small. An atom, for instance, emits specific, discrete bands of colored light based on the highly constrained rules of its internal energy states. But the hardware running a superconducting quantum computer operates on a different premise. Instead of studying subatomic particles, we are forcing massive, human-made electrical circuits to exhibit those exact same quantum behaviors. To understand the physical scale we are talking about, look at this device. It is a fabricated electrical chip measuring a full centimeter across. The voltages and currents surging through it are driven by Avogadro's number of moving electrons. If you take a macroscopic circuit like this, remove all internal electrical resistance, and freeze it to near absolute zero, that entire collective swarm of electrons obeys the laws of quantum mechanics. This demonstrates that quantum mechanics is a broad, universal framework. We can engineer robust quantum systems from the top down, using classical electrical engineering rather than solely observing them at the subatomic level. The driving force controlling this artificial atom is the microwave photon. It acts as the discrete quantum of electromagnetic energy, operating at roughly 5 gigahertz. The primary vulnerability of this system is that the energy contained in a 5 gigahertz photon is roughly 1 million times smaller than a photon of visible light. At room temperature, that tiny control signal is easily drowned out by ambient thermal noise. To isolate that microwave photon, the ambient temperature must drop drastically. We achieve this using a dilution refrigerator, built with massive, tiered golden cooling stages that pull the system down to a fraction of a degree above absolute zero. Even at those extreme temperatures, ambient noise from room temperature control electronics can cascade down the physical wiring. Engineers must design specialized microwave filters on every control line to strip away stray thermal energy before it ever reaches the chip. Operating a quantum computer demands extreme signal-to-noise isolation and precise, low-temperature microwave thermal management. This animated diagram illustrates a baseline classical circuit, a standard copper inductor and capacitor acting as a harmonic oscillator. Beside it, you see its resulting parabolic energy well, characterized by equally spaced horizontal energy levels. If you apply a continuous radio frequency signal to this circuit, it steadily absorbs that energy, pushing the state continuously upward across these uniform levels. Because the physical gaps between the energy levels are identical, any microwave frequency that pushes the system from the bottom state to the first state will also indiscriminately push it into the second, third, and fourth states. This continuous linear absorption makes it physically impossible to isolate the circuit into a distinct binary 0 and 1. To function as a bit of quantum information, a system must respond to highly specific, discrete bursts of energy, absorbing only what is required to move between two dedicated states. A linear oscillator cannot function as a qubit because its energy states cannot be uniquely addressed by a single targeted microwave frequency. The hardware solution requires breaking the linearity of the system. We do this by replacing the standard inductor with a specialized component called a Josephson junction, which warps the symmetric parabola into an asymmetric cubic energy well. A Josephson junction acts as a highly nonlinear kinetic inductor. Because it is built from superconducting metals, it operates with zero electrical energy loss. By warping the potential well, the junction compresses the physical spacing of the upper energy levels. This creates an isolated, distinct 5 GHz gap that exists solely between the ground state and the first excited state. That isolated frequency gap prevents energy from cascading upward, successfully turning the macroscopic circuit into a uniquely addressable two-level system. In the 1980s, physicists validated this behavior by sweeping a 5 GHz microwave generator across a cooled macroscopic circuit, specifically looking to see if they could force it to jump between these discrete levels. The recorded data showed a flat baseline trace interrupted by sharp, distinct voltage spikes, proof that the circuit was absorbing energy in strict, quantized packets. Integrating this non-linear Josephson junction into a standard LC circuit successfully transforms the classical circuit into a macroscopic artificial atom. With an addressable two-level system in place, moving the qubit between the 0 and 1 state requires highly calibrated bursts of 5 GHz microwaves. Sending a precise, complete microwave waveform acts as a quantum NOT gate, pushing the system entirely from its resting ground state up into the excited state. If we carefully shape the waveform to deliver exactly half of that energy, we apply what is mathematically defined as a square root of NOT gate. This animated block sphere shows the result. Applying a half pulse physically forces the macroscopic circuit state vector to rotate exactly halfway between the 0 at the North Pole and the 1 at the South Pole, creating a 0+1 quantum superposition. To prove this logic holds, applying a second identical half pulse continues the rotation along the exact same arc, landing the state perfectly on the 1 at the South Pole. The physical shape of that superposition relies heavily on the phase of the incoming microwave. Altering the phase dictates the precise rotational axis the state follows as it moves across the sphere. Early laboratory setups used simple continuous wave microwaves, but generating high-fidelity superpositions requires precise digitally defined arbitrary waveform generation. To achieve this control, engineers integrated advanced vector network analyzers and dedicated digital-to-analog converters directly into the quantum laboratory. They apply standard control engineering principles and precise impedance matching to iteratively optimize these pulse shapes, driving up gate fidelity. Maintaining high-fidelity quantum control translates abstract superposition into the rigorous practice of digital-to-analog RF waveform shaping. Driving a single artificial atom is a resolved engineering problem. The objective now is scaling those individual nodes into a massive, tightly synchronized computational array. Sustained focus. Because physical qubits are inherently delicate and highly susceptible to noise, integrating comprehensive error correction across the array is an absolute necessity. To detect and repair these continuous errors, the prevailing architectural blueprint is an algorithm known as the surface code. This animated diagram illustrates the physical constraint of the surface code. Every individual qubit must be mapped into a precise two-dimensional square grid, wired strictly to its immediate nearest neighbors. Restricting the connections to a 2D layout allows engineers to map the entire array directly onto standard semiconductor chip formats, making hardware scaling technologically feasible. This specific grid constraint enabled the design of the 53-qubit Sycamore processor, the chip used to execute an algorithmic calculation faster than the world's leading classical supercomputer. Transitioning from laboratory experiments to a functional quantum computer requires translating abstract error correction theory into a concrete, manufacturable 2D hardware layout. The mathematical elegance of a 53-qubit grid relies on massive, unwieldy physical infrastructure. Every individual qubit currently requires its own dedicated microwave control line, creating a severe radio frequency routing bottleneck where hundreds of thick coaxial cables crowd the interior of the cryogenic fridge. Furthermore, current qubit production heavily relies on liftoff processes from decades ago. At a massive scale, this results in high failure rates and inconsistent junctions. To build larger arrays, the industry must adopt the highly precise, subtractive manufacturing techniques used for modern 300mm silicon wafers. The ultimate hardware goal is monolithic cryogenic integration, printing complex microwave routing directly onto adjacent silicon wafers to replace the bulky wiring of the golden chandelier. This introduces extreme material engineering challenges. To manage the temperature load of high-density wiring, engineers must force standard silicon to conduct heat as effectively as copper at temperatures near absolute zero. The path to a commercial quantum computer now lies in solving these industrial fabrication and extreme environment electrical engineering hurdles.